When we drop an object, we see something that starts motionless at zero velocity, but clearly moves, i.e., has non-zero velocity later. In other words, the object's velocity is changing. So by watching the motion and knowing our fundamental principle, the non-zero velocity changes we see here suggest that the total interactions, represented as a total force, a net force, are also non-zero. We recall that earlier we said that F net is the vector sum of all the significant pushes and pulls from the surroundings acting on our system. So to predict the motion future here for this falling object, we will need to be able to model each of the important interactions, the forces from the surroundings acting on our system, and therefore contributing to F net. So that's what we'll discuss now. The first step to modeling forces is to identify them. This can be surprisingly challenging for the simple reason that we can't typically see a force. So a good place to start in a particular situation is to identify what agents in the surroundings can exert a force on our system. Here, to get started, we're going to rely on our past knowledge and common experience. We'll refine these as we go along. So starting with our case of a falling object, let's begin by identifying one interaction, one force that we think may be involved. Our experience and knowledge tell us that the Earth interacts with the object via gravity. So the Earth is the first agent we identify that can exert a force on our system. That force which the Earth exerts is a gravitational force we commonly call weight, and which we will label as vector W. And we may also refer to this as the weight force for extra emphasis. To construct a model for this vector quantity, we know we need to be able to describe both the magnitude and the direction. Let's handle the direction first. Here we're dealing with an object near the Earth's surface, so, from common experience, the direction of the weight force is down. Now we can take one more step here and say we are going to specify a coordinate system with our axis oriented vertically. We will make a conventional choice here by choosing to label this axis as the y-axis, and we'll choose up to be the positive y direction. That's the direction specified by j hat, the y-axis unit vector. We emphasize here that there are a number of other choices of axis labels and axis directions that we could make that would be equally good. For this choice, though, we can specify the direction of the weight force, w hat, in terms of j hat. W hat is equal to minus j hat. We still need to specify the magnitude of W. From common experience, we know that the weight is approximately constant. Moreover, we know that oftentimes when we weigh an object using a measuring device like a scale, instead of reporting the magnitude of the weight force, the device often reports a different physical quantity, the mass of the object. Here the device relies on a model for the magnitude of the weight force, which says the magnitude of W is proportional to the mass of the object. The words "is proportional to" are equivalent to saying that the magnitude of the weight force is equal to a constant times the object's mass, where we'll use the letter little g to represent this constant. G is positive and has the approximate value of 9.8 meters per second squared near the Earth's surface. G can be interpreted in different ways, including ties historically with falling objects and objects rolling down inclines all the way back to the time of Galileo. We will later describe what G means in terms of a more fundamental description of gravitation, but for now, it's part of our model for the weight that expresses how strongly the Earth pulls on an object of a given mass m. So now we have all the ingredients for modeling weight, which, as for all vectors, we can express as the product of the magnitude and the direction. Combining all the results from what we just discussed, here's our model for the weight force. In many physics courses, weight is often taken as the only force, the net force that acts on falling objects. However, we're not going to stop here because that's not realistic for many situations in the real world. For example, skydivers would be in big trouble if weight were the only force acting on them as they fall from the sky. What is another interaction, another force that skydivers and many other falling objects experience? Clearly, the atmosphere, the air can often exert a significant force, an air resistance force, or as we often call it, a drag force. Let's discuss how to model the vector drag force, which we will represent with the symbol F sub d. Just like our model for the weight force, we'll handle the direction and the magnitude of the drag force separately, motivating each from our everyday experience. Now, we don't need to fall to experience the drag force. Anytime we ride a bike or travel in a vehicle that is open to the air, we can often feel the drag force. These kinds of experiences tell us about the direction of the drag force. It's always opposite to the direction we're moving. We can tie that direction to the direction of a vector quantity that is always associated with the motion of the object. What would be a good choice for this vector motion quantity? The answer is the velocity vector. Remember, we said that v hat, the direction of the velocity vector, always gives the direction the object moves. So if the drag force always points in the direction opposite to the direction of motion, we can express the direction vector f d hat as minus v hat. What about the magnitude of the drag force? Well, one thing we notice from riding a bicycle or traveling in a vehicle open to the air is that the faster we go, the larger the drag force. So it appears the magnitude of the drag force depends on the speed, the magnitude of the velocity. There are lots of possible ways to express this. We'll try choosing a model that probably is the simplest. Let's try a model where the magnitude of the drag force is proportional to the magnitude of the velocity, or in other words, the magnitude of f sub d is equal to a constant, which we'll call b, times the magnitude of the velocity. By dimensional analysis, b must have the units of newtons times seconds divided by meters in the SI system. But what else can we say about b? What does it depend on? What is its value? The short answer is that we might expect b to depend more fundamentally on the details of the airflow, which in turn could depend on properties of the object's shape and size perhaps. For our purposes, we'll treat b as a parameter whose constant value will determine for the particular falling object that we'll study. We'll discuss how to do that later. So now we have all the ingredients for modeling the drag force, which is the product of the magnitude and the direction. Combining all these results from what we have just discussed, here's our model for the drag force, where we notice that the product of the magnitude of the velocity and v hat is just the velocity vector v. Let's be clear about one thing. Although our model here tells us the drag force depends on the object's velocity, both the direction and the magnitude, this does not mean the object is pushing or pulling on itself. The drag force comes from the surroundings, specifically the air surrounding the object, exerting a force that is on the object. If there was no air, there would be no drag force. B would be equal to 0, regardless of the object's velocity. So now we have in hand models of forces that the surroundings can exert on a falling object. We are now in a position to look at a real-world example of a falling object and apply our fundamental principle to understand and to predict motion. We'll do that in our next lecture.